Now let's take a look at the concepts of sequences and series here. Sequences and series. Alright, so what are these two terms here? What do they mean? Well, first of all, a sequence is nothing more than just a list of numbers. So think of a sequence. So think of a sequence as a list of numbers. This list can go on forever, meaning that a sequence can be infinite, or it could come to an end, which means the sequence is finite. All right, but let's look at some examples here. Examples of sequences. Again, sequences are just nothing more than a list of numbers. Keep that in mind. So, for example, here's a finite sequence: 1, 3, 4, 2.7, 5.8. Right. So here's a sequence of 5 numbers here, right? Five numbers or 5 terms. So this is a finite. So it comes to an end of just 5 numbers. Finite sequence of 5 terms. 5 numbers. Each number is called a term. 5 terms. All right. First number is the first term. Second number is the second term. Third number is the third term, and so on. All right. Let's take a look at an infinite sequence and maybe see what the pattern is also. So there may be sequences with that go on forever, and also has a pattern to it. Excuse me. So let's take a look at this one. Here's something simple here: 2, 5, 8, 11. Okay, so maybe you start to see the pattern here, right? The sequence starts at 2. First term is 2, right? And then the next term is 5, and then goes to 8, and then goes to 11. Next one's going to be what? 14, right? 17, and so on. As you can see, the numbers are increasing by what? By 3. Right? When it's increasing by a constant, there's a special term for this type of sequence. But the dot, dot, dot means it goes on forever. We'll talk more about these types of sequences next time. But anyways, this is an infinite sequence because it goes on forever. Just to give you some terminology here. Infinite sequence, all right, and has a pattern. All right, the pattern is what? It's increasing by 3. Here's a more complicated sequence. All right, so let's look at this one. 1, 2, 3, 5, 8, 13. So and so on. All right, so here's another infinite sequence. This pattern is more complicated. This is in fact called the Fibonacci sequence, a very famous sequence in mathematics. All right, this has many applications in nature as well as the financial markets. But anyways, let's look at what the pattern is, right? So it starts off at 1 and 1, but look at the starting with the third term, 2, and then this one's 3, and then goes to 5. Now look at the 2 here, the third term. I can find that by adding up 1 and 1. Look at the 3. I can find this by adding 2 and 1. Look at the 5. I can get 5 by adding 3 and 2. Look at 8. I can get 8 by adding what? 5 and 3. 13, I get that by adding 8 and 5. Then the next term is going to be what? Well, found by adding 13 and what? And 8. So it's going to be what? 21, and so on. But anyways, yeah, so starting with the third term, every term after that, starting with the third term, every term is going to be what? The sum of the previous 2 terms. Okay? That's what the Fibonacci sequence is. All right. So the next term after 21 will be what? 21 plus 13, what? 34, for example, and so on and so forth. All right. So that's a famous sequence in mathematics, something to keep in mind here down the road. But anyways, let's look at the general sequence here. All right. Let's look at the general sequence. Let me go and clear up the screen. So we mentioned the first number is the first term. So here's the general sequence then. General sequence. Alright, the general sequence is going to be what? Written as A1 for the first term, A sub 2. These are subscripts. These are not exponents now, right? A sub 2 for the second term, A sub 3 for the third term, A sub 4 for the fourth term, A sub 5 for the fifth term, and so on. Alright, so again, these are subscripts, not exponents. Alright, these are just telling you that this is the first term, this is the second term, here's the third number, fourth number, fifth number, and so on. Now, the general term is called the nth term. So this is called the nth term, or the general term. Typically, there's going to be a pattern for these types of sequences. So you might be given a formula for the general term. All right. So for example, let's say I give you this formula: a sub n is equal to n squared plus 3n minus 5. All right. And I want you to find. Let's find, given this general term. So typically, if there's a pattern, it's defined in terms of n, right? And I want you to find a sub 7 and a sub 10. In other words, find the 7th number on this list, find the 10th number on this list. Well, as you may suspect, this is not a hard problem, because all we do then to get the 7th term and the 10th term is to plug in the 7 for n, plug in the 10 for n. Right? So this is nothing more than plugging in. Not bad at all. So a sub 7 is going to be what? 7 squared plus 3 times 7 minus 5. So this is going to be 49 plus 21 minus 5. That's going to be what? That's going to be 70 minus 5, or 65. So this is the 7th term. If I were to write out the numbers, this is the 7th number in this sequence. And what's the 10th number? Well, plug it in, right? So 10 squared plus 3 times 10 minus 5. So 100 plus 30 minus 5, or what? 125 is the 10th number in the list. Okay? So to find if you're given the nth term, it's not hard to find any term. You simply plug numbers in for n, as you can see, right? Let's go and try another one. Let me go and clear up the screen. Suppose I give you this one here. What about a sub n is equal to negative 1 to the nth power times, let's say, n squared. All right, and I want you to find the 5th term and the, let's say, the 12th term. All right, find the fifth number and the 12th number if the sequence has this pattern to it. Well, again, just plug it in. So a sub 5 is going to be what? Negative 1 to the 5th power times 5 squared. Now, negative 1 to the 5th is what? Negative 1, right? So that's negative 1 times 25, 5 squared, right? Or negative 25 for the 5th term. What about a sub 12, or the 12th term in the sequence? Well, that's negative 1 to the 12th power then, right? Times 12 squared. Negative 1 to 12 is what? Positive 1, right? This is positive 1 now, because a negative number to an even power is positive. Times, what's 12 squared? 144. So this is just 144. Alright? So again, not too hard. If we're given the nth term, we simply plug it in to find out what is the number in that sequence. Alright, anyways, let's take a look at series then. Let's look at the concept of series here. Alright, now a series is just a sum. It's the sum of a sequence. So we see the word series, think add. Sum is a sum of the terms. Oops, sorry about that. Sketchpad's acting up. Of the terms in a sequence. In a sequence. Alright, so think of series as the word sum. So you're adding something up. So now, then let's go ahead and take a look at this series here. Alright, so I want you to let me just give you one real simple: 1, 2, 3, 4, and 5. Here's 5 terms. I want you to find the series. Find S5. Add up these 5 numbers, right? So that's just going to be 1 plus 2 plus 3 plus 4 plus 5, right? So that's going to be what? 6 and 9. That's going to be 15. Alright? So series is what? Addition here. Now, typically though, we'll write the sum in what's called sigma notation. Let me give you that concept here. Let me go clear up the screen. So for example, if I want to add up 1 plus 2 plus 3 plus 4 plus 5 we did earlier to get the 15, right, as our answer. I could have written that as the summation. So here, this is sigma notation here. This is called sigma, the Greek letter sigma notation. When you see this notation, you're thinking addition, you're thinking series, right? Of, let's say, k going from 1 to 5. I'm adding 5 numbers here of k, all right? So that's what this is. 1 plus, when k is 1, you plug it in. So when k is 1, the term is 1. When k is 2, the second term is 2, so 1 plus 2. When k is 3, plus 3. When k is 4, plus 4. When k is 5, plus 5. And that's where you got the 15 that we saw earlier. All right. Now, what if I give you a different pattern inside here and change these numbers around? So, for example, let's go ahead and find this sum. Some sigma notation. Let's say k going from 3 to, let's say, 3 to 5 of k squared. Let's go and find that one. Well, to figure out what this sum is, again, this is adding numbers together, we have to first plug in the numbers for k from 3 to what? To 5. So this 3 is the lower limit of the sigma notation. All right. This 5 is the upper limit of the sigma notation. But again, all this means is what? We're plugging in k going from 3 to 5 and then adding up into this k squared pattern and then adding up the numbers. So let's do that. So that's going to be what? When k is 3, you're going to get what? 3 squared plus, right? So sigma means plus. When k is what? 4 next, so you get 4 squared plus when k is 5, you get 5 squared. All right? So this is nothing more than 9 plus 16, 4 squared, plus 5 squared, 25. So this is what? 25 plus 25, or how about 50, is the sum. All right? So we can figure this out just by plugging numbers in. Not too bad at all. Let's go ahead and try another one here. Let's go and evaluate this sum of k going from 4 to, let's make it 4 to 9 of, let's say, how about 3k plus 1, right? So here's a different pattern for us, right? So let's plug in 4 through 9 for k into this 3k plus 1 pattern and add up the numbers. Sigma means what? Add them up. So let's do that. When k is 4, start with 4k, right? So what's that going to be? Let's do that in our heads a little bit. What's 3 times 4? 12, right? Plus 1? 13. So if the first term we're going to start adding from is 13, because k started at 4, right? 4, again, 3 times 4 plus 1, 13. Plus, let's plug in 5 for k. Next term, you plug in 5, right? So when k is, so this is where k is equal to 4 for the first term. Now k is equal to 5 for the second term. What's 3 times 5? 15, right? 15 plus 1, 16. So this is when k is equal to 5, right? Plus, let's look at k equals 6 now, right? Next number, next k is going to be 6. 3 times 6 is what? 18 plus 1, 19. You can probably see a pattern here, by the way. It's just increasing by 3, by the way, right? But we'll plug it in just to be more specific here. All right. This is when k is equal to 6. You get this 19 as your number for this pattern. What about k equals 7? Next up is 7, right? 3 times 7 is what? 21. Plus 1, 22. So this is when k is equal to 7. All right. Plus, let's continue down here since I'm running out of space. When k is 8, it should be 25, right? Well, it is, right? 3 times 8 plus 1. 24 plus 1, 25. This is when k is equal to 8. And lastly, we finally get up to the upper limit of 9. When k is 9, you should get what? 28. When k is equal to 9, because it's just increasing by 3. So 3 times 9 is what? 27 plus 1? Yeah, we do get 28. So what's that equal to in the calculator again? I'm just going to punch this in the calculator instead of adding it by hand. 13 plus 16 plus 19 plus 22 plus 25 plus 28. 123. So the answer is 123 for this sum. But let's talk about the number of terms here based on sigma notation. Here, if I go from 1 to 5, how many numbers am I adding up? Well, we can see 1, 2, 3, 4, 5 numbers. 1 through 5 means what? You're adding up 5 numbers. If you go from 3 to 5, how many numbers is that? Well, 3 to 5 is what? 3 numbers, 3 terms. How about 4 to 9? 4 to 9 is what? 1, 2, 3, 4, 5, 6 terms. So here we have 6 terms to add up. Here we have what? 3 terms to add up. And here we have 5 terms to add up. So in other words, if I give you some sigma notation, how do you figure out the number of terms you have to add up? Well, not too hard, turns out. Look at this pattern here. See if you could figure this pattern out. But here it is. Take the upper limit minus the lower limit. What's 5 minus 1? 4, right? But add one more to it to get the number of terms. So the number of terms here is what? 5 minus 1 plus 1. So 5 terms. 5 minus 3, 2 plus 1. So 3 terms, or 3 numbers to add up. 9 minus 4 is what? 5 plus 1, 6 terms to add up. Alright? So let's go and try another one so you can figure out a number of terms here. Sigma of k going from, let's say, 6 to 12 of 2k. Let's make the pattern simple for us to add up. Alright? But you'll go from 6 to 12. So how many terms is that? Well, again, number of terms to add. The number of terms in a series, right, meaning the sigma notation, right, is equal to the upper limit, in this case the 12, minus the lower limit, in this case the 6, plus what? Plus 1. Alright? So how many terms do we have here? 12 minus 6 plus 1, or what? 7 terms, 7 numbers to add up in this series. But regardless, you're plugging in k going from 6 to 12 into 2k to figure out what the actual terms are that you need to add up. So that's going to be what? Just doing our heads here. When k is 6, 2 times 6 is what? 12. K is 7, 2 times what? 2 times 7, 14. Plus when k is 8, 16. When k is 9, 2 times 9, 18. Continue here. Plus when k is 10, 2 times 10, 20. When k is 11, 2 times 11, 22. When k is 12, the 7th number we're adding is going to be 24. 2 times 12, 24. Can we see there are 7 numbers to add up here? Again, just punch it down to the calculator. 12 plus 14 plus 16 plus 18 on the calculator, plus 20 plus 22 plus 24. We get 126. Alright, so just punch in the calculator carefully, add up the numbers carefully. Not a big deal. So pretty easy to work with in terms of the sigma notation here. Not too bad at all. Alright, let's look at then this problem then, right? So let's look at the sigma of k going from, let's say, 4 to 7. And how many terms is that? Right? There's what? 4 terms here, right? Of kx. Let's go and add up. Find out what the sum is. Well, that's equal to what? 4x. Remember, you're plugging in for k, not x, right? So x stays x. All right, stays a variable. In other words, you're plugging in for k, not for x. So 4x plus what? 5x plus 6x plus 7x. Can we see I just plug in from 4 to 7 on k on the coefficient of x in this case. So 9x plus 6x is 15x plus 7x is 22x is the solution. Alright? So not too hard at all in terms of working with sequences and series. Sequence is just a list of numbers. Series is when you add up the numbers in the sequence. So think of the sigma notation for that. Alright, let's go and finish out. We'll give you some problems to try and post in the Blackboard. Let me go clear out the screen here. Alright, so number 1, let's work these problems out here to finish out here, so if you will. Alright, so let's suppose I give you the general term an is equal to negative 2 to the nth power over n plus 1 times n plus 3, and I want you to find the 7th term in that sequence. Alright, find a sub 7. Just plug in, basically, right? Not too hard at all. And let's evaluate these two series here. Evaluate the sigma notation of n going from 3 to 8. So I'm using n instead of k. This is really the same thing. 5 minus 2n. Here's the pattern to plug in n from 3 to 8 and add up the terms. And last but not least, let's evaluate the sum from k going from 2 to 6 of ln of k, natural log of k. Plug in and add up these logs for me. All right, so go ahead and work these problems out carefully and post the solutions into Blackboard. All right, so until next time then.